Our strategy for computing volumes of the n-dimensional simplices is the same as that of a cone. We're going to slice in a direction parallel to the base. And what we're going to see is that when we slice an n+1 dimensional simplex, what we'll get is an n-dimensional simplex whose size is rescaled by a factor of x in each coordinate, where x is the distance to the top of the simplex. So, for a one-dimensional simplex, the appropriate volume element of the slice is nothing more than dx. In a two-dimensional simplex, the appropriate area element is what? It's simply x dx. In the three-dimensional case, well, we've done this before. This is going to be 1/2 x times x dx. And in general, the difficult step is to argue that the volume element for the n+1 simplex is the volume of the base n simplex v sub n times x to the n, since we're rescaling each coordinate by a factor of x. But once we have that, and then multiplying by the thickness, dx, we can compute this n+1 dimensional volume as the integral of the volume form. That is, the integral of v sub n times x to the n dx, integrating as x goes from 0 to 1. This is a trivial integral since v sub n is a constant. We obtain x to the n+1 over n+1, evaluated from 0 to 1. That gives us v sub n over n+1. And so we can write down all of these volumes by induction and argue that v sub n is in fact 1 over n factorial. That's a nice application of simple integration. Let's move on to an n-dimensional ball of radius 1. These are a little difficult to draw. In 2D, this is simply a disk of radius 1. In 1D, it's a disk of radius 1. Well, it's really an interval of length 2. And in 1D, it is, again, a simple point. Higher dimensional balls are not so easy to draw. Now, how do we define it rigorously? The unit ball is defined as those set of points with coordinates x sub I between -1 and +1, satisfying the additional constraint that the sum of the squares of the coordinates is also less than or equal to 1. This is what we're used to in 2D when we say x squared plus y squared less than or equal to 1. This is simply the generalization of that. Now, in terms of a slider bar analogy, now all of the individual bars can go from -1 to 1. Each can go to the very top or the very bottom. But in between, well, you have some freedom to move the individual sliders up and down, but you can't move them all past a certain point where the sum of the squares is less than or equal to 1. Nevertheless, it feels like there's a lot of room inside of there to move around. How do we compute the volume? Well, again, for a radius 1 ball in dimension n, what is the volume going to be? In dimension 0, there's a single point, volume 1. In dimension 1, this interval has length 2. In dimension 2, well, we know the formula, pi r squared. In this case, r equals 1. In dimension 3, volume is 4/3 pi. Moving up to dimension n, well, what are we going to do here? Let's call that volume of the unit ball v sub n. And to determine what that is, let's consider what happens when the radius is not 1, but r. In this case, the length of the one-dimensional ball is 2 times r. The area of the two-dimensional ball is pi r squared. The volume, 4/3 pi r cubed. In general, having a ball of radius r in dimension n is going to give you the volume of the unit ball times r to the nth power. And that's going to be helpful for us, as we'll see. The surface area is what? Well, in the one-dimensional case, it's 2. In the two-dimensional case, we're looking at the circumference. That's 2 pi r. In the three-dimensional case, the surface area of the ball is 4 pi r squared. Do you see a pattern? Yes, it's related to the derivative. In fact, it's going to be, in the n-dimensional case, n times v sub n times r to the n minus 1. You'll be able to prove that result in multivariable calculus. What's the diameter? Well, in all cases, it's equal to 2 times r, or in the unit case, 2. Now, let's see if we can figure out what this n-dimensional volume of the unit ball, v sub n, is. Well, we're not going to be able to prove it in here. We'll do it in the bonus lesson. Suffice to say that with some work, one can show that the volume of the n-dimensional ball of radius 1 is, when n is an even number, let's say 2 times k, then the volume is pi to the k over k factorial. When n is odd, that is 2k plus 1, then the volume is pi to the k factorial 2 to the n over n factorial. Whew, that's kind of complicated. We'll show you how to get this in the bonus material. But for now, the question I want you to consider is, what happens to the volume of the unit ball as the dimension increases? Well, let's see. N, and thus k, are getting bigger and bigger and bigger. But there's a factorial in the denominator. What happens then? This means that the volume does not get bigger as the dimension increases. In fact, the volume goes to 0 as dimension increases. And it goes to 0 rapidly, since factorials beat powers. This is cause for some alarm, for some puzzlement. What does this mean? Well, let's think in terms of the difference between a ball and a cube in dimension n. Let's say we have them fight. Who wins? Well, in low dimensions, the ball of radius 1 definitely has more volume or area than the cube of side length 1. This is true in 2D. It's even true in 3D. But it is not true in all dimensions because of those corners in the cube. Those corners eventually stick out from the ball, even when the two are concentric. And all of the volume inside the n-dimensional cube lives in those corners. That's why cubes beat balls. This lesson was neither short nor simple. It may take a little time for things to sink in. Don't worry. You're not going to be asked any questions about hypervolumes of balls on the final exam for this course. And in our next lesson, we're going to return to the more familiar low-dimensional world. But step back for a moment. Think about what you've done. We have, with rational thought and calculus, measured objects that you cannot see, smell, taste, touch, or experience with your senses. That's not a bad day's work.